when force acts on an object, we say that when force acts on an object and the object is able to move a certain distance, we say that work has been done on that object, or we say that the force has performed work. So work is actually force applied times displacement. When I apply a force on a certain object or on a certain body, and that body is able to is able to displace from a point to another, is able to move from a point to another point, we say that that force has performed work on that object. So that's how we say it. Now, force can do different kinds of work. Force can do positive work, and force can do negative work. What do I mean? When a force decreases the speed of an object, that's a negative work. When a force increases the speed of an object, that is a positive work. So force actually, you know, force acts in different ways. Force can make an object to speed up. Force can decrease the speed of an object. That is, if the force is acting in the opposite direction to the motion of the object, it can decrease the speed of the object. So that is a negative work. So force generally increases the kinetic energy of an object. If the kinetic energy of an object increases, that is a positive work. If the kinetic energy of an object decreases, that is a negative work. Force can also help an object to change direction. Yes. If I apply a force, I will show you different concepts or different cases of application of force on an object. And I think we have five. So I will show you the different cases and you will see how force affects the speed of an object, or how force affects the kinetic energy of an object. So, but generally, force is equal to, I'm sorry, generally work is equal to force times displacement. We say that work is done when a force applied on an object causes the object to move or to decrease or to change direction. So that is that. So anytime you are asked or you are given a question and you are asked to calculate force, sorry, and you're asked to calculate work, if you are given the force applied and you are given the displacement, that's the distance moved, you can calculate your work done. Now, the unit of your work is joule. I'll give you that. The unit of your work is joules. So let me give you that. J. The unit of force is Newton, and the unit of displacement is meters. So if I give my work in joules, I am correct. Or if you are giving work in joules, or if you are solving question and you give your answer for work in joules, you are correct. And if you are solving your questions and you give your answer for your work in Newton meters, you are still correct. So the unit of force is Newton, the unit of displacement is meters, while the unit of force is joules. So now let me now show you the different cases of application of force and on an object and what it does, whether positive or negative work. But before I go there, I want to show you that both force and displacement has as vector. Vector just means the magnitude and the direction. So force has a direction and it also has magnitude. Displacement also has direction, it also has magnitude. So when the displacement vector and the vector of the force, when they are in the same direction, something happens. When they are in opposite direction, something happens. When they are inclined at an angle, something happens. Or when they are in perpendicular to each other, something happens. So I will show you the different um case or the different scenarios of application of force on an object and what that force does when in each case. So let me show you. Now in the first case, if displacement is in this direction and force is also in this direction, this FA means applied force. So if an object, let me show you in a diagram. If an object is moving in this direction and I apply a force in the same direction of the object's movement like this, we say that the force and the we say that the force and the displacement vector is parallel to each other. Look at this. this is moving in the same, this is moving along this direction. Displacement vector is along this direction. The action force is also along this direction. So we say that they are parallel. Now, anytime the displacement vector and the action force, anytime they are parallel or anytime they are both traveling in the same direction. Now, look at this object. Let's assume it's a football. Football is going forward, or let's assume it's a small boy running. You are running forward, and I apply a push along the same direction. What happens? So we say that since the boy is running in this direction and I push the boy in that same direction, not too much of push, just a little push along that same direction, we say that, now I will show you what happens, but I can tell you now. What happens is that the boy speeds up, or the car speeds up, or the football speeds up. So let me show you. Now, the angle between, look at it, they are parallel to each other. So the angle between them is 0 degrees, since they are parallel. And you can calculate the work done. Now, the formula of work done is force times displacement cos theta. Now, work done is equal to force times displacement cos this theta is this 0. Now, if you check in your calculator, if you check force times displacement, if you check cos 0 in your calculator, you are going to get 1. So you multiply this by 1. Work done is force times displacement times 1 will give you force times displacement. Now, cos 0 is going to give you positive 1. If you use that positive 1 to multiply force and displacement, you are going to get positive. So, meaning that this force is doing a positive work. This force is doing a positive work on this object. What that means is that anytime a force is doing positive work, it will increase the speed of the object. So Ke, that's kinetic energy. Kinetic energy of that object will increase. Remember that we said that kinetic energy is the energy that a moving object has, or a moving body has. So when an object is moving at high speed, or when an object is in motion, we say that that kind of energy possessed by that object that is in motion is kinetic energy. So when a force, and when an applied force, when a force is applied in the same direction of the motion of the object, it's going to try to speed up the object. So it's just giving it an additional push in that same direction. It's going to help it to speed up. So kinetic energy of that object will increase because I'm applying a push, and that is a positive work. Actually, when you apply force on an object, or you are doing something, when you apply force on an object, you are transferring energy to that object. So when you transfer energy to that object, it has more energy. It's actually moving before. It has a kinetic energy with which it's moving. But when I apply force, I'm adding energy to that energy, so it helps it to speed up. So that's what happens, and this is the first case. So let us go to the second case. Case number 2, when an applied force is in this direction, but the displacement vector is in the opposite direction. Let me show you in a diagram. Let's assume that an object is, or let me do it this way, so that let's assume the displacement vector is in this direction and I apply the force in opposite direction. So let's assume this object is moving in this direction and I apply a force in opposite direction. We call this force, we call it pull. The other one we considered the other time is push. So we are pushing. When you apply force in the same direction of the motion of a body, you are pushing. But when you apply force in the opposite direction, you are pulling it. So this object is moving in this direction, and I'm applying a force that is pulling it in the opposite direction. So this one, we say that it is opposite. So the displacement vector and the applied force, they are both in opposite direction. So the angle for this, if you are in opposite direction like this, the angle is 180 degrees. If you want to use that to calculate your work done, this will be force times displacement cos theta. This will be force times displacement cos 180 degrees. If you check cos 180 in your calculator, you are going to get force times distance. Cos 180 degrees is going to give you -1. If you use that here, it's going to give you minus negative force times displacement, and that is just telling you, this minus sign is telling you that this force is going to do a negative work on this object. So if this object is moving in this direction, if I pull it back, I'm going to reduce the speed. So here we say that kinetic energy is reducing. Kinetic energy will go down. The other time I said that when you apply a force can do a positive work, it can do a negative work. No, so this is an example of a force doing a negative work on a particular object. So if somebody is running in this direction and you come behind the person, you pull the person towards you, that's a negative work because you are going to reduce the speed with which that person is running. So that's the second case. Let us check the third case. Now, this is the third case. The third case is if I have my displacement vector in this direction and I have an action force at an angle, at a particular angle. Let me show you. If a boy is running in this direction and I apply a force, I'm pulling the boy up a little bit. Yeah, not directly. So this force is not parallel and it's not opposite, but it's inclined at a particular angle. So what happens? Now, your angle is, in this case, your angle can be between 1 degrees to 89 degrees. Yes, your angle can be between 1 to 89, meaning that it can be 1, it can be 2, it can be 3, it can be up to 89 degrees. So any angle between, or let me just say, any angle between 0 degrees to 90 degrees. Yes. So let me give you like this. Any angle between 1 degrees to 89 degrees. Let me do it that way. So if you calculate the work done here, it's going to be force times displacement cos theta. So your work done will be force times displacement cos. Now it's going to be any theta. It's going to be any angle. It can be 1, it can be 2, starting from this one up to 89. It can be 1, it can be 2, it can be 3, it can be 4, it can be 5, it can be 70, it can be 60, it can be 30, it can be 6, it can be. So I want to assume that let us just take 30 degrees as an example. So this one will be 30 degrees. So your work done is going to be force times displacement. Cos 30 is going to give you okay, let me use 60 because 60 is going to give us 0.5. So this is 60. So cos 60 is going to give us 0.5. Now, we don't really need this 0.5 here. For this explanation that I'm doing, what I actually need is this positive or negative? As you can see here, it's going to give you positive answer. So since it's going to give you positive answer, this is plus. So this force is doing a positive work on this object because if you look at it in a way, this action force is almost in the same direction because I'm running. Let's assume the boy is running in this direction and I'm pulling the boy towards that direction. The force is not really parallel, but then I'm still pushing the boy in that direction. So it's going to still be positive work, and the kinetic energy also is going to increase. Anytime you have a positive work, anytime a force is doing a positive work, is going to increase the speed of that object, or is going to increase the kinetic energy of that object. So that is that for this particular case. This is case number 3. Let us check the next case. Now the next case is case 4. So if you have the displacement vector in this direction and the force applied in this direction, what happens to the object? Look at it. Let's assume the object is going in this direction and I apply a force at an angle but in the opposite direction. This is the angle. Now our angle for this case, our angle must be between 91 degrees to 179. So I can choose, if you want to calculate the work done for this, it's going to be force times displacement cos. I want to choose, let me choose maybe cos 120 degrees. Let me choose 120. So your work done for 120 is going to be force times displacement, open bracket. If you press cos 120, you are going to get minus half or minus 0.5. Now, I don't really need this 0.5 for this particular thing I'm explaining to you. What I need is this sign that is here. So from here, we have seen that this force is going to do a negative work on this object. So this is W equals to minus, and work is, so this is a negative work, And because it's a negative work, your kinetic energy is going to reduce. The kinetic energy of this object is going to reduce. That is, how fast it's moving is going to be reduced. The speed of that object is going to be reduced because the object is going in this direction and I'm pulling the object in the opposite direction, but inclined at an angle. So, but it's still going to reduce it. So that's a negative work. And this is the fourth case. Now let us check the fifth case. Let us see the fifth case. Now, in the fifth case, we have if you have your displacement vector in this direction and your applied force inclined at exactly 90 degrees. Inclined exactly at 90 degrees. Let me give you an example. So the boy is running in this direction and I'm pulling the boy exactly or directly upwards. I'm pulling the boy directly upwards, or I'm pulling the boy sideways. Let me say it that way. If I'm running forward on a track, maybe with full speed, and somebody is trying to pull me on the side, not a great force, not a kind of great force. The person is pulling me, or maybe let's say something is just pulling me to the side. That's a 90 degree because I'm going in this direction. The force is pulling me in this direction. That is, the force is perpendicular to my direction or to my displacement. So what will happen? Let's see what happens. Now, your theta for this is going to be 90 degrees. Look at that. Then your work done is going to be force times displacement cos theta. Your work done is equal to force times displacement, open bracket, cos 90 degrees. This is cos 90 degrees. Work done is going to be force times displacement. Cos 90 degrees is going to give us 0. If you check it, you are going to see that. Now, W is equal to force times displacement times 0 is going to be 0. So what this means is that the force is doing no work on this particular object. 0 means that the force is doing no work, meaning that it's not going to speed up the boy, it's not going to slow down the boy. The only thing it's just going to do is that it's going to change the direction of the boy. So the kinetic energy is neither increasing nor decreasing. What happens here is that direction changes. Direction changes. So if I keep applying this force, if I don't remove it, I'm going to change the direction of the boy. And if I don't remove the force, the boy will end up circling around. If I don't remove that force, it's going to end up circling around. It's like a circular motion. Or no, it's like a rotatory motion where an object is fixed to an axis and is forced to circle around or to rotate around. So there is that string that is holding the object to an axis, or the object, let me put it that way. The string that is holding the object to an axis is like this force. So once this force is there, the ball keeps rotating around, rotating around, rotating around, rotating around. So that's what happens. So when a force is applied at 90 degrees to a moving object, it's not going to slow down the object, it's not going to speed it up. The only thing it's going to do to the object is that it's going to help the object to keep changing direction. And if that applied force is still there, it's going to start circling around that axis. So this is what happened, and these are the 5 cases. These are the 5 cases. So now let me show you this. Now I said that work done is equal to force times displacement cos theta. So it means that if you have if you are given a question and the force is inclined at 90, it means that no work is done, no work done. Direction changes. Direction changes. So put it like that. Then if it is 180 degree, what happens here? If your force is applied 180 degree, it's going to be negative work. Negative work. Negative work. Now, if it is 0 degrees, this is going to be positive work. Now, also, if it is from 0 degrees to 89 degrees, 0 degrees to 89 degrees is still positive work. But if it is from 91 degrees to 179 degrees, this is also negative work. So if you are given a question and you are given an angle of inclination. Just check. Is it 90? Is it 180? Is it 0? Is it between 0 and 180? Or is it between 91 and 179? So whatever the angle of inclination that you are giving, whatever it is, that determines whether it is a positive work or it's a negative work. So that is that. So I said where now look at this formula. W is equal to work done, and F is equal to force applied, and it can also be load. Yes, it can also be load. Yeah, if I carry a load, if a load is lifted, if I'm able to lift that load, it means that I've applied enough force that should be able to lift that load. So the force that I'm applying, you may be given a question, and in that question you may not be given the force, but you may be given the weight of the load, or you may be given the load itself. So it means that if you are able to lift a load, it means that you have applied enough force to be able to lift that load. So the weight of that load is the same force that you are applying. So they may not even talk about force at all in your question. They may just talk about the weight of the load. So the weight of the load is also the force that you applied. Because if you don't apply enough force to a particular load, you may not be able to lift it. Do you get that? If you apply enough force to a load, you'll be able to lift it. So the weight of the load is the same force that you're applying to carry it. So there are some questions that will be given to you. They will not mention force, they will mention load. They will not mention load, they may not even mention load, they will mention weight. Just know how to be able to calculate or maneuver or understand what they are saying. So D is displacement. And of course, theta is equal to angle of inclination of the applied force of FA, angle of inclination of FA. So once you know all this, you can calculate your work done. Okay, so let us quickly go to power. So let's quickly go to power. What is power? Power is defined as the work done. So if you know your work here and the time it takes to perform that work, so power is work done over time. Or power can also be defined as energy consumed over time. So now that is power. Power is the amount of work you did and the amount of time it took you to do it. So if I can do a particular kind of work, if I can do it faster, I have more power because my time will reduce. Now, but if I take a lot of time to do a particular work, I have lesser power. So power is talking about how fast you do a particular work, or power is talking about how fast I'm consuming a particular energy. So if I supply an electric energy and I'm consuming it fast, it means I have high power. Yes, so that is how it is. Now, the unit of power is where P is equal to power. Power is the rate at which work is done. Power and is measured in watt. Then, of course, W. So I can write this one as W over T, or as energy over time. So it can be like that. So where W is equal to work done, you already know, and T is equal to time. So work done is in joule. It can also be in Newton meter, while your time is in seconds. Yes, so that is that. Power is equal to work done over time, or it can also be energy consumed over time. And for short, you can write it as W over T or E over T. Now, your power is measured in watts. Watt is spelled as W-A-T-T, and you can see it as just W. And then this one, work done, is measured in joule, and you can see it as J, which is for joule. Joule is spelled as J-O-U-L, joule. And this is Newton meter. That's if you want to use the SI unit. And then your time, of course, is measured in seconds. So that's how you can do that. Now, so power is usually given in So if you are giving power like this, 1 kilowatt, 1 kilowatt is 1,000 watts. You may be giving 1 megawatt also. 1 megawatt. If you see 1 megawatt, 1 megawatt means 1 million watts. So that is how it is. That is it. So now I've explained energy and work done and power. So let us. But before we go on to question, I want to show you energy. I want to show you something about energy. Now, when I was explaining energy, I was saying when I was explaining energy, we have different kinds of or forms of energy. But I want to identify two that I want to talk about now: kinetic energy, kinetic energy, and potential energy. Now, so I said kinetic energy is an energy due to motion. So if an object is moving, it has kinetic energy due to the fact that is moving. Then potential energy is an energy um uh, possessed by a body by virtue of its position. So let us assume that an object, look at my hand, let's assume that an object is suspended here at this height, and another object is suspended right above it. So now the one that is higher, when it lands on the floor, can do more work than the one that is below it. Why? The reason is because this one is at an higher height compared to this one. So the more the height of an object to the ground, the more the potential energy. If an object is far above the ground and you release it at that height, as it drops through the space, it gains more speed. So by the time it hits the floor, it will have enough energy to do work compared to another object that is not really very far from the ground level. So that is potential energy. Just potential energy is energy due to position of an object. So we denote kinetic energy as Ke, and this is what the formula to measure it. Kinetic energy is half mv square, where m is equal to mass of the object, and v is equal to speed of the object or velocity of the object. So that is that. And kinetic energy is measured in meters, because kilogram. Now mass is for kilogram. That's kinetic energy. Yeah, the unit of kinetic energy is mass is kilogram, and this velocity is meter square per centimeter square. So you can be like this. Then potential energy, PE. Potential energy, we have different kinds of potential energy. We have the gravitational potential energy, we have the elastic potential energy, we have the electrical potential energy. But we will not talk about the elastic potential energy and the gravitational potential energy. Oh no, we will not talk about the elastic and electrical. But under here, we will talk about the gravitational potential energy, because that's the one. That one is, those other two, they are specific, but this one is more general. So let's talk about that one. Gravitational potential energy. I was explaining the other time that when an object is at this height to the ground and another object is at this height to the ground, by the time they fall to the ground, the one that is at higher height is going to do more work than the one that is at lower height because of their different positions. So it means that I can calculate the potential energy of an object by using its mass, multiplying it with the gravitational field strength and the height. This G is acceleration due to gravity. So where m is equal to mass in kilogram, then G is equal to acceleration due to gravity, and h is equal to height. This one is meters per second square. This one is height above the ground and is measured in meters. So here is the formula for kinetic energy. Here is the formula for potential energy. And I also gave you another example of energy that day. I called it mechanical energy. Mechanical energy is the addition of kinetic energy and potential energy. So let me write it here. Mechanical energy is denoted as Ma. Ma is the addition of kinetic energy and potential energy. So if you are given the kinetic energy and potential energy of a particular working machine or instrument or whatever, if you can add the two together, that will give you the mechanical energy of that particular object.